So we were discussing regarding the analysis of machine foundation, and obviously we saw that there are 6 degrees of freedom, 6 degrees of freedom, and there are 4 modes of vibration. And the first one we started to analyze, so we have used the analogy of weightless spring. So we have considered the soil to be composed of weightless springs, and we have to analyze in that way. So the first thing is we have to analyze what are the forces, the motion of the simple harmonic motion undergoing the mass, which the mass m is undergoing when it is connected to a spring of spring constant k, and it is given a displacement of z max. So it is given a maximum displacement of z max. So amplitude is z max. So the amplitude of the motion is z max. So that will determine what will be the force acting on the mass at the most distant points. So that is at the amplitude. So similarly there will be another in this way. So we saw that initially the spring was here in the static case. Alright, so the mass was not attached. As soon as the mass was attached, so there was a displacement of delta static. Okay, so here in this condition we have k delta stat is equal to W. Now when this mass was given a displacement of Z max and then released, so somebody took hold of this mass, pulled it down up to the Z max position and then left it. Now we are not concerned with how much force he applied during the pulling and what time it took. That part we are, for now we are just neglecting. Alright, so we are just concentrating on as soon as the person releases the mass. So from that time what will happen? So obviously this will be the force acting on the mass. Now we know W is equal to K delta stat, so we can neglect, cut off this two. Alright, so we can, these two will negate each other. So ultimately we have a force Kz. So we know, so force is equal to mass into acceleration. So here Kz equal to m into double z. So this is the equation of motion for this spring system. Alright, without the dashpot. Okay, so this is the spring system. So another thing is that we know when the mass connected to a spring, it is left to vibrate on its own, so it will undergo simple harmonic motion. So it will undergo simple harmonic motion. So the simple harmonic motion, the displacement function, alright, the z at any time t, so the z at any time t, we can approximate as a cosine or a sine function. So obviously the initial phase will depend on where from we take the time t. Okay, so we have discussed that. So the displacement function, here in this case x it is written, here in this case it will be z. So whatever you take, ultimately it is the displacement function, and at any time t we can we can write the displacement function as a cosine or a sine function. So the thing is that the particle will undergo a motion of this sort, so it will go up and down, and while that the projection of that particle will undergo a uniform circular motion. So we can now define the frequency of, or the angular velocity of the particle, and we can say that at any time t the displacement of that particle will be sine of omega t. Now if t Here it is alpha is equal to 0. Alright, the phase is 0. If we consider t at such a position that the particle is somewhere here, so from there we measure the t, so we can say, so the particle will, the displacement function will be of this sort. So we can say at that point that this is the theta, so we can say plus theta. So that is the displacement function. At any time t, what will be the displacement of the particle? Now if we differentiate the displacement, we will get the velocity. And we saw that the velocity is at a phase difference of pi by 2. Okay, so or 90 degree. Then if we differentiate the velocity, we will get the acceleration of the particle at any time t. So at any time t, we have the displacement z. If we differentiate the z with respect to time, we will get the velocity. If we differentiate the velocity with respect to time, we will get the so at any time t, z is the displacement, so dz by dt, differentiating with time, we will get the velocity. At any time t, differentiating the velocity, we get the acceleration. So that is what we saw. So we have the natural time period, we have the natural frequency, and we can define the natural frequency as omega n root over k by m. So we saw that we can draw a phase diagram. So this is the displacement phase, this is the velocity phase. Okay, so the maximum displacement is z naught, so in this case, so it may be z max. Alright, so that is the maximum displacement. So in this case, this, alright, so that is the maximum displacement from the equilibrium position. Alright, so in this case, this is the maximum displacement from the equilibrium position. This is the equilibrium position. So this is the equilibrium position. So that this is the maximum displacement. Similarly here, this is the maximum displacement. So we draw the phase for the displacement. Then we have the velocity component. And we saw here, so that is the maximum value of the velocity will be omega into z. Okay, so omega into z. That is the maximum value of the velocity. Maximum velocity, that means. And where will the maximum velocity be? At which position? We saw that the maximum velocity is here. So you can see it stops, accelerates, stops, accelerates, maximum velocity at this position. Accelerates, stops, changes direction, accelerates, stops, decelerates. So as it comes down, accelerates, stops, alright, and then as it goes down here, so the velocity reduces and it stops. Okay, so that is where the maximum velocity is, and obviously the acceleration is opposite to the displacement. So now how to draw the force? So we have already discussed F is equal to ma. So F is k into z naught. So k into z naught will always be opposite to the displacement. So this will be the k into z naught, which is the spring force. So the force of the spring, okay, the force in the spring. So the force in the spring. So that is k into z naught. Opposite to that, we have the mass into acceleration. So this is the inertial force. Alright, so mass into acceleration. So this is acceleration. Okay, omega square z naught. And if we have a despot system, so the despot will always act opposite, the despot force will always be opposite to the velocity. It will always oppose the motion. Alright, so the force, since the velocity is in the upward direction, the force from the despot will be in the downward direction. And that will be equal to C, which is the despot coefficient, C, into the velocity, which is omega into z naught in this case, in the phase diagram, that is. Okay, so here what we can do is, so if we want to vary with time, so we can write it like this: m omega square z naught. Okay, so it is in phase with the displacement. Okay, so we can write sine omega t. Okay, so the force at any time, or the inertial force at any time. Okay, so kz naught will be in the opposite direction, kz naught. So sine of omega t plus pi so at any time t, what is the force from the spring? What is the inertial force at any time t? That means this will undergo all of this phase. It will remain at the same phase difference. The phase difference will be same. This phase difference will be same, but it will undergo circular motion. So that is how we get the displacement curve, velocity curve, and acceleration curve. Okay. So in a natural system, as we have discussed, so we always have some sort of damping, and when a displacement is given to the system, so gradually there will be some motion, sinusoidal or simple humming motion, but ultimately that motion will damp out due to the damping effect of the soil. So that is what the dashpot system does. It reduces the motion, and ultimately the motion it damps out, all right, or it dies out. So this is the force diagram, and here we have a force acting. So F naught sine omega t is the force which is acting on this system. So F naught sine omega t. So it is of this system. So Q equal to Q naught, that is F equal to F naught sine omega t also we can see. So this is the force which is acting. So this is applied sinusoidal force. Okay, and the system, it will first respond in this manner. So the response of the system will be in this manner. So ultimately what will happen is that the vibration of the system, it will, because of the damping effect, it will ultimately die out. Okay, but thing is that this applied frequency, it will continue to be in motion, right? So the system ultimately will vibrate with this applied frequency omega. Okay, so basically what happens is that, so there is initially at the start of the motion there is superposition. So superposition, so this we have a1 sine of omega t plus beta plus a2 cos of omega n t plus a3 sine of omega n t. So ultimately the actual motion of the system will be summation of this motion plus summation of this motion. Okay, ultimately what will happen? This motion will die out and only it will continue to vibrate with the frequency of omega. Okay, so for that we have, so we have this phase diagram, and ultimately we can draw a phase diagram similarly for the system, this system, that is where it is acted upon by F naught sine omega t. Okay, so ultimately we have mass into acceleration plus c into velocity plus k into z is equal to the applied force F naught sine omega t. Okay, so as we have discussed here, as we have already discussed here. So this is Z0, so we will have K Z0 in this direction, M omega square in this direction, omega square Z0 in this direction acceleration, and C omega Z0 in this direction. Okay, so this is K Z0. So the total force will be of the system will be K Z0 minus M omega square Z0. So this is one component. Okay, this minus this will be one component. So that will be K Z0 minus M omega square Z0. So that is one component. The other component will be C omega Z0. So we will have a resultant. We will have a resultant, and that will be exactly opposite and equal to the applied force. So this will be F0 and this will be F0, the applied one. Okay, and this is the reaction from the system. So action, this is the action here. So this is the applied action and this is the reaction from the system. Okay, so from here itself, if we know to draw the phase diagram, from here itself we can find out various properties that we need. First of all is the maximum amplitude Z0, because F0 or Q0, whatever you say, alright, that is the maximum force from the applied system, so that is already known. Alright, so the manufacturer of the machine, he will give you those data. So when the machine will be operated, it will exert maximum amount of F0 force or Q0 force, and omega will be the frequency of operation of the machine. So those data will be already given by the manufacturer of the machine. So the thing is that we have to find out omega n and Z0 of the system, so that we can control Z0. That is our main idea. Alright, so we have to control Z0. The amplitude has to be within permissible limits, and we have to control omega n such that there is no what? Resonance. Okay, there is no resonance. So first of all, let us find out what is F0. It can be easily found out. So if this is, suppose this is so this is suppose A and this is B and C we consider. So it is A square is equal to B square plus C square. Alright, so here what we have, F0 square is equal to, so K minus omega, so that is K Z0 minus M omega square Z0. So that is square. Alright, and this is plus C omega Z0 square. Okay, so Z0 square, Z0 square, Z0 square, we can take it out. So ultimately we will have K minus omega square, omega M minus M omega square plus C omega square, that is. Okay, this is also square. So whole into, we can write here Z0 square. This Z0 square is taken out. Alright, so ultimately we will have F0 is equal to root over K minus M omega square plus C omega square. Okay, into whole into Z0, whole into Z0. So what is Z0? So Z0 is equal to, that is the maximum amplitude, is equal to the force applied by this. So that is Z naught. So easily from this phase diagram we can find out. So if the system does not have damping, so this component will be 0, this component will be 0, and we will have F naught by root over K minus M omega square. Okay, so easily we can find out. And then this angle phi, the resultant, alright, the direction of the resultant. So that is also an important. So phi is equal to phi is equal to y by x, we can say. So y, this is y. Alright, so if this is phi, if this is phi and this is y and x, so phi is equal to, or tan phi basically, so tan phi is equal to y by x, we can say. So what is y here? So tan of phi we can write here C omega Z naught. Okay, and what is x here? K minus M omega square. Z naught, sorry, into Z naught. So Z naught cancels out, and we have phi is equal to tan inverse of C omega by K minus M omega square. So that is the resultant phase. Okay, the resultant phase with the this one. Okay, so with the displacement we can say. So the resultant phase with the displacement of the force, applied force, that is. Okay, ultimately phi will depend on the applied force and the response of the system, that is. So if there is no damping, if there is no damping, so you can say that phi is equal to 90 degree, that is. Alright, so because this will be 0 if there is no damping, so tan inverse of 0 we have 90 degree, pi by 2. Alright, so that means the force applied will be opposite to, in this direction, that is. Okay, so that is a condition of resonance. So that is why some amount of damping is required. Okay, some amount of damping is required to control the amplitude when there is a resonance. So that is, of course, we will see that in the coming slides. Now here we can define certain important terms in the analysis. Okay, so in the analysis we can define certain terms. So just now we have defined Z naught is equal to F naught by root over K minus M omega square plus C omega. Right, just now we have defined that. This is square, of course. Right, so this is also square. Okay, so this is what we have defined. Now what we do is we divide F naught by the spring constant of the system, that is the K. Alright, so F naught by K. So we divide it by F naught by K. So here also the K will come, so this will be K square. Alright, so K will be here. So again K will be here and K will be here. Okay. So this F naught by K is the static deflection. So initially the spring was in this manner. Okay, then suddenly we apply the force F naught. Okay, and then it will come to this position here. So this is delta stat. Okay, so delta stat is equal to k into, k delta stat is equal to F naught. So k into delta stat or static is equal to F naught. So we have F naught by k is equal to delta static. Okay, so we have F naught by k is equal to delta static, and we can write it like this now. So now we can write it like this: Z naught is equal to delta static by root over 1 minus, so this is m square omega square by k square if we write, right, and this will be c omega by k square. Now if you remember, omega n is equal to root over k by m. Okay, so omega n square is equal to root over omega square n is equal to k by m. Okay, so m by k, so m by k is equal to 1 by omega n square. Alright, so that is what we will replace here. So, and delta stat we will bring here. So z naught by delta stat is equal to, here it will be 1, and this will be 1 minus omega by omega n square plus cw by k square. Okay, so we have defined two important terms. Alright, so z naught by delta stat here, this term is the magnification factor, is called the magnification factor. Okay, and omega by omega n is called the frequency factor. Alright, or you can say frequency ratio as well. So this is frequency factor or frequency ratio, whatever you say. Alright, frequency ratio. So these two terms, this term magnification factor and frequency factor, is the guiding parameter while designing the this foundation system for the machine foundation. Okay, so that is what we have to control. So obviously if there is significant damping, so we can see it quickly dissipates. There is no frequency, no vibration, sorry, there is no vibration. But if there is less damping, then there is vibration, and obviously thing is that if there is significantly lesser damping, so there will be significant amount of vibration, right? So we have an overdamped system. So here these are the overdamped system. So this is critical damp. All right. So within like this it is stopped. All right. So in the overdamped system, the force transmitted to the foundation is significantly high. All right. So the force transmitted to the foundation is significantly high when it is overdamped system. Okay. Then we have the underdamped system. So in that case, there will be vibration of the foundation system, and of course the critically damped when we have it is the damping is equal to the component from the spring mass, spring system as well. All right. So another important factor is when we have a damped system, so we have the damped natural frequency omega d. Now when the damping is significantly high, so the omega d comes into play. When the damping is significantly low, so we can consider that the damped frequency is also equal to the natural frequency. So ultimately, basically, we are neglecting this. Okay, so we are saying that it is almost equal to the natural frequency. So this we have already discussed. So this is the plot of the magnification factor versus the frequency factor. Okay, so frequency factor versus the magnification factor. So here you see, as the frequency of the operation of the machine, it tends to the natural frequency, we have high amplitude. Okay, so Z0 is increasing, so we have very high amplitude for the same amount of force and the stiffness of the soil. So we have high amplitude. So Z is increasing. So the thing is that we have to keep in this range. Alright, in this range we have to keep. Now in that range, if you see the effect of the damping, so it is much lower compared to what it is in the resonant case. So damping comes into play when the system is operating near the resonant frequency. Alright, so when the natural frequency, when omega of the system, the machine frequency, operational frequency of the machine is equal to the natural frequency of the system, so then there is the problem, and then the damping comes into play. If there is good amount of damping, then the amplitude can be controlled in a much, the amplitude is much smaller. Right, but thing is that generally we are in this range. Right, so the damping does not have a much effect to play. So that is why in most of the analysis of the machine foundation, what we do is we generally neglect the damping. So here we see, so we have the frequency factor and we have the magnification factor, and this is the phase angle, the phi, with frequency factor, alright, or frequency ratio. So this is the combined motion of the system. Alright, so we have Z is equal to, so here we have the delta static by frequency factor, and we have two motions. So here you see sine omega t, sine omega t, omega t. Okay, so omega is the frequency of operation of the machine. Okay, and sine omega t is the natural frequency of the system. And this Z is the combined displacement function for this two superimposing motion. Okay, so we have two imposing motion. So we have Q naught sine omega t, we have that force, and we have the omega n natural frequency system. Okay, so the two forces are, the two motions are superimposing, and we have the total displacement Z in this manner. Okay, so we have to avoid this condition at all costs. So we have to avoid this condition. So this is the condition when C is equal to 0. Alright, so here if C is damping is equal to 0, so we have one curve in this manner and the other curve in it will be like this. Okay, it will be like this. So this is the frequency. Alright, so that this is what happens. So as we have just now analyzed, so phi is equal to tan inverse of this C omega z naught by k minus m omega square z naught. Okay, so z naught cancels out and we have C omega. So when C or the damping is 0, so we have phi is equal to 90 degree. Okay, so the force, it is in this direction. So it is phase angle is 90 degree for all values of damping, right? So this is a critical condition, all right, and the maximum amplitude at this condition. So we can say, so it is, we can say, so here you can see C omega z naught is equal to f naught. So we can say here C omega z naught is equal to f naught. So z naught is equal to f naught by C omega. Now C omega is 0, so z naught tends to infinity. Alright, it is infinity. So that condition we have to, stop at all condition. Okay. So now, up till now, we have been considering F naught force. So if there is a rotating body, so we have already discussed here. So in that case, the force will be radially outward. So when it is at the downward position, so the force will be downward from the mass, rotating mass, and when it is upward position, it will be in the upward. And we will have two components. So mainly when it will be here, so only one component will be there, and in the other positions, so here what will happen is that the force will be in this direction, and for this one the force will be in this direction, so it will cancel each other out. Alright, so the total force which will be applied to the foundation will be in this manner. Alright, so it will be sinusoidally varying in this manner. So in that case, the Q naught force or F naught force, we express it in terms of this. So twice ME, so 2 ME. So ME is the rotating mass, ME is the rotating mass, right? So 2 ME, E into omega square. E is the eccentricity, right? So this is the eccentricity, E is the eccentricity, and we have omega square is the frequency of rotation. So this is omega, how it is rotating. So we have twice m e omega square. So Q naught is equal to twice m e omega square. Okay. So when we plot it for the magnification factor versus the frequency factor, so for Q naught, so we had a value of 1 here, right? Because Q naught has a certain amount of, it is not dependent on the frequency, alright? So Q naught is not dependent on the frequency, whereas here it is dependent on the frequency. Therefore, when the frequency is 0, that is when the machine is not operating anywhere, so it starts from the 0 component. Okay, so that is why this difference. But other than that, the other parts of this curve or this plot is similar. Okay, so it is similar. So here you see it is in this range, so it is in this range. Okay, so this is a normalized curve. All right, so that is why it is similar. Okay, so that is, I mean, this is normalized for the displacement, or displacement by displacement. Okay, so displacement by displacement, so that is why it is. And this is also a factor, so factor versus factor, magnification factor versus frequency factor. Okay, so now why we are discussing, we have already discussed that. So thing is that omega, which is the operating frequency of the system, and mass of the system will all be given. Okay, now what we have to determine is, we have to determine the spring constant, and if there is any damping, we have to determine the damping. Of course, as we will see, basically, since we are considering, I mean, higher variations in the frequency of operation and this natural frequency, so therefore thing is that the damping, since it is not very effective, so it is considered that there is no damping, it is neglected, damping is neglected, right? But thing is that we now have to obtain the, I mean, the spring constant for the various motions. So as you recall, if you recall, so we have the Z rotation motion, Z translational motion about Z, then we have the rotation motion about the Z, then we have the translation motion about X or Y axis, and we have the rocking and pitching motion about Y or X axis. Okay, so what are the things that we need to determine? We need to determine Cu, which is coefficient of elastic uniform compression, that is Cu. Then we need to define what is, uh, so this is Cu. So for Z we have the Cu. Then for translation along X or Y axis, we need to define C tau. Okay, so that is elastic, uniform elastic coefficient for uniform elastic shear. Okay, so that is what is C tau. Then we have then we have the coefficient for non-uniform compression, C phi. So when there will be rocking and pitching, we observed that there will be non-uniform compression and motion. All right, so that is C phi, and obviously we also need to find out C psi. Okay, so C psi is basically the coefficient for non-uniform shear. All right, so when there is rotation about the Z axis. So finding out C phi and C psi is a very difficult process. So mostly the emphasis is on this uniform elastic compression, and then we correlate that to the various properties. All right, and of course C phi also, C tau also we can obtain by, if we do the horizontal block shear, I mean the horizontal vibration, horizontal block vibration test. So then we can obtain the C tau. So that also we can obtain. But IS code, IS 5249, I think. So it gives the correlation between the various properties. So Cu, that is coefficient of elastic uniform elastic compression, so that we can easily obtain by plate load test. So plate load test. So we have already discussed that. So plate load test, what we do, we have a plate, we load it up to certain value, release it, again load it up to certain value, release it, again load it up to certain value, release it. Okay, again load it up to certain value, release it. So that is why cyclic plate load test. Cyclic plate load test. Okay, so we have a plate which is put on the ground and it is loaded and released and loaded. So ultimately, if you see, we have some amount of elastic compression and some amount of plastic compression for a particular load. So we take this elastic compression and we plot it against the load. Okay, so elastic settlement in mm by load intensity. So we will have this coefficient of uniform elastic compression. Okay, so this is the coefficient of elastic uniform compression. So from the cyclic plate load test, we can obtain that. Then apart from that, we can do the block vibration test. So either it is vertical vibration, all right. So vertical vibration, or it may be horizontal vibration as well. All right. So if it is vertical vibration, we will obtain Cu. If it is horizontal vibration, we will obtain C tau. Okay. So thing is that we change the frequency. We change the frequency. The frequencies of operation is changed. It is increased, and the amplitude is noted. So we will have a maximum amplitude at a particular point. So we will have the maximum amplitude at a particular point. So that will give the natural frequency of the system. So that will give the natural frequency of the system, omega n. Or basically it will give the damped natural frequency. So omega n is equal to, omega d is equal to omega n into root over 1 minus d square. Okay, but we can neglect this and we can consider this to be the natural frequency. Okay, we have the eccentricity of the mass defined, we have the frequency of operation, and we have the maximum amplitude. Okay, from there we can also obtain what is the natural frequency. So that is one of the important and aspect of the block vibration test. All right, so for especially for designing of machine foundation, and not only that, knowing the dynamic properties of the soil, so block vibration test actually is a very important test. So ultimately we have the frequency and mass of the system. All right, so those are supplied by machine manufacturer, and we need to obtain the spring constants of the soil, various spring constants of the soil. All right, so the spring constant we can say Cu. One is Cu, that is elastic uniform compression. So C tau, uniform shear, C phi, non-uniform compression, and C psi. Okay, non-uniform shear. So these are the properties that we have to determine from the test. Apart from that, we have to determine what is the natural frequency of the system and what will be the maximum amplitude that will occur in the machine foundation or in the foundation, in the machine itself. All right, so all combined, machine, foundation, and everything combined, what is the maximum amplitude and the maximum frequency. So this is the criteria we have to again fulfill. So static load, no shear failure, no settlement. All right, so general foundation system, and in dynamic loads, no resonance, omega by omega n should be greater than 1, permissible amplitude Az, all right, and annoyance from vibration should not be there. All right, so we have these limits defined. So that is what we have to fulfill. So we have already discussed when we consider the soil for the for the first mode of vibration, that is when the soil we have the spring here like this and the motion is along the z axis. So the motion is along the z axis. That is the first mode of vibration, that is for uniform compression. Okay, so similarly we have for the sliding vibration of a block. Okay, so ultimately we have a block, so we can again define the same equation. So we have, in this case we have x. So what we will consider is, as we have discussed earlier, we will consider the mass to be attached to some springs in this direction, that is. Okay, and the stiffness of the spring is kx, suppose. Okay, if the stiffness of the spring is kx, or like total combined stiffness of the spring is kx, so if it displaces x in this direction, so we have the force in the mass due to the spring kx into x. Okay, so and then we have the inertial force, that is m into acceleration. So in this case the acceleration will be in this direction, so x is the displacement, dx by dt, that is x dot will be the velocity, and d square x by dt square is equal to x double dot will be equal to the acceleration. So that is kx into x plus mx is equal to, we have this force acting. Okay, so px into sine of omega t. So as we earlier defined, f is equal to f naught sine omega t. So that means here px is the maximum force. Maximum, the magnitude of the force, and it is varying with time with this sinusoidally. All right. So definitely at one point it is 0. All right, and at other time it will be px. All right. So it will vary from px to px, and at some point it will be 0. So it will be sinusoidal with time. Okay, so this is the equation of motion. So now at any time t, so let us consider the maximum this displacement. All right, so the maximum displacement is at okay, first of all we have already defined, so m x square plus kx is equal to px sine of omega t. All right, so for the natural part of the system, for the natural frequency of the system, we will have mx plus kx is equal to 0. So this equation will satisfy the natural vibration of the system. So we have frequency omega, natural frequency in the x direction, all right, for translation. Okay, natural frequency in the x direction for translational motion, remember that. So there will be rotation also, we will consider that afterwards. So this is for translational motion x t. So we will have k, so here if I write kx, so kx by m. Okay, kx by m. And what is kx? So kx we can write it as the area into the coefficient of elastic uniform shear, that is C tau. All right, coefficient of uniform elastic shear, or coefficient of elastic uniform shear. All right, so C tau. So C tau into A is kx. So that is how we define that. So ultimately we will have omega natural frequency in this direction. For translational motion in the x direction or y direction, whatever you say, it will be equal to C tau into A by m. Okay, so that is the natural frequency. Of course, if you want to find out the frequency in terms of hertz, alright, so that will be 1 by twice by omega n. Okay, as we have discussed just now in the earlier slides. So you can find out the frequency in terms of hertz. So this is angular frequency and this is the frequency in terms of numbers of cycle. Okay, numbers of cycle, that is. So now let us consider the point where it is at the maximum displacement. Okay, so it is at the maximum displacement. So it is so if I consider, suppose, this spring here. Okay, so this is the equilibrium position, and from here, so this M, it is moved on to this position here, and this is, suppose, X max. Okay, so this is X, capital X, that is, so that is X max, that is X max equal to capital X. Okay, so that is basically the amplitude. So we have to find out the amplitude. Now at this position, so at any time t, we have just now defined m into acceleration so the forces which are acting, all right, so kz, all right, so force is kx in the x direction plus px sine of omega t, so equal to mass into acceleration, you can see. Okay, so F is equal to ma, we know. Bit. So it will be easier if we come from that equation. So we know F is equal to m into a. So what is F? One is k into x, kx in this direction, that is, so kx into displacement x. The other is this px plus px sine omega t. Now x is a function of time, remember, okay? So x is equal to capital X sine omega t. Okay, capital X sine omega t. So at any time t we have x displacement. So the time is already included in this small x. Alright, so that you keep in mind. And we have px sine omega t is equal to mass into acceleration at any time. Okay. So what is the maximum amount? So here at this maximum displacement we will have the maximum force acting. So we will have kx into capital X. So it is at the maximum displacement. So if you remember that now there is this. So if you remember the phase diagram, so we had k minus m omega square and c omega z naught. Okay, so this is z naught, and we have f naught. Now, and this is f naught. So this is the reaction of reaction from the system, and this is the applied force. Okay, so now we have this component as 0. So we have f naught is equal to k minus m omega square. Okay, so here what will happen is that, so we will have px, and here we will have m into the acceleration. Okay, so what is the acceleration? So we can say that to be omega n square, m omega n square, or omega n square x, sorry. All right, so omega n square x, omega n square x. So that will be the maximum inertial force. Okay, and this is the applied force. So now this is the applied force. Now what we can do, we can equate this. Okay, so here so kx we can replace it with, sorry, this will be omega n square. Okay, so this will be omega square, and k, so we know k is equal to root over, sorry, omega n is equal to root over k by m. Okay, root over k by m. So omega n square is equal to k by m, and k is equal to omega n square m. Okay, so that is what we will place here. So omega n square m into x plus px equal to m omega square x. Okay, so ultimately, so px, we will take it out that side, so this will come this here, this side here, so we have m, so mx we can take it out, so m into x we can take it out, omega n square minus omega square, so this we have taken this side and this will go that side, equal to, this will be actually plus or minus px, ultimately this will be px. Alright, so we can, this will be actually minus here, this will be minus. Okay, so this will be minus here, so mx omega n square minus omega square and equal to px. So if you remember, so we have f naught in this direction and k minus m omega square into z naught or x, whatever you say, in this direction, and this will be px. Okay, so equal to this, so k is equal to this. Okay, so we have put it there. So ultimately x, which is the maximum amplitude, is equal to p naught by, so m omega n square minus omega square. So when omega, that is the frequency of the operation of the machine, it tends to the natural frequency, so this will become equal to 0. Alright, so x will tend to infinity. Alright, so that is what is to be prevented. Okay, so ultimately we can find out what is the maximum amplitude of the system right from this equation. Okay, so the rest we will discuss tomorrow. We will stop here.